So we are going to go ahead and look at example 5 from lesson 9 in AP Physics. We're given a couple pieces of information from the problem. We're given the force required to compress the spring by a certain amount. All right, and then that in a launcher, the launcher is then going to launch a ball of a particular size horizontally. We're looking specifically at the ball's speed when it exits the launcher. When we do that, we're going to go ahead and want to set up a little bit of information. So I have my wonderful handy dandy launcher. Inside of it is my ball that I am launching. Behind the ball is my compressed spring. All right. When the spring is allowed to uncompress or to expand to its relaxed position, it's going to be at the end of the launcher. In which case it will be at equilibrium. When it's at equilibrium is that final position for it. I'm going to go ahead and set that to 0 meters. That helps make my life easier in the end when I start pulling equations. That compressed length, however, is going to be my initial position for my spring, and that is my 0.15 meters. So you may have noticed I went ahead and converted from centimeters to meters, get that all in base SI units to make my life easier. To put everything else in base SI units, I'm going to go ahead and look at the mass is going to be, instead of grams, in kilograms of 0.045 kilograms. All right. So just getting this question, you might be a little confused. You might not know what to do next. Well, we just learned just before we got to this particular problem that the work done by a spring is equal to that 1/2 kxi squared minus 1/2 kxf squared, right? So xi is the initial amount of stretch or compression, xf is the final amount of stretch or compression. And typically, you do see final quantities minus initial quantities, but this is related to the potential energy of a spring, which we will get into more depth for in lesson 10. So that goes ahead and sets this up. If we are looking at the total work done by the forces in a system, we know that work total is equal to my change in kinetic energy, or my final kinetic minus my initial kinetic, right? In this particular case, the only work done is by the spring itself, and that's because we are launching the ball horizontally. If we know that my ball is going to be moving across, whereas my weight is straight down and my normal force is straight up, those are both perpendicular to my displacement. Therefore, the work done by those particular forces is 0. Right? So then I'm going to go back to the fact that the only work done is going to be the work done by the spring. It's going to be our work total, and we are going to be relating that to the change in kinetic energy. The ball is initially sitting in the launcher at rest. Right? Because the ball is initially sitting in the launcher at rest, it doesn't start with any kinetic energy. So this initial kinetic energy is 0. Right? When the ball gets to the end of the launcher, my spring is now entirely relaxed. So my final position of that spring is also 0. As a result, I'm left with this term and this term. Right? So my total work is the work done by the spring, which in this particular case is the 1/2 kxi squared, and that's equal to the final kinetic energy. We know that kinetic energy is equal to 1/2 mv squared. In this particular case, it's our final velocity. We are able to go ahead and simplify this equation a little bit because we do have 1/2 on both sides, so they do cancel. And when we rearrange for speed, since that's what we are looking for, we do finally get this due to the magic of algebra. right? We know the mass of our ball. We know the amount of compression of our spring. The only thing we're missing here is our K. Remember, K is our spring constant. And that does come from the other pieces of information we were given. We're given the force required to compress it by that much. Well, that actually brings us to something we learned a little bit sooner than that, and that's Hooke's law. The force required is proportional to the amount of stretch or compression. Well, that proportionality is the spring constant. So that K is equal to force divided by amount of compression. So that 4.8 newtons divided by 0.15 meters gives us a spring constant of 32 newtons per meter. All right, so now we have everything that we need. We can go ahead and plug everything into our speed equation. Our speed is equal to my amount of stretch or compression of 0.15 meters times the square root of 32 newtons per meter divided by 0.045 kilograms. From here, when I plug everything into my calculator, I do get an answer of 4 meters per second. All right. So that is the answer for this particular problem. The second part of the problem, you may recall, says what happens if we now shoot the ball vertically. Well, if we now shoot the ball vertically, the total work is not just done by the spring. Now there is work being done by gravity. As a result, the gravity is going to be opposite the displacement. This number is actually going to be less. We will talk about how to solve that a little bit more thoroughly when we get to the next chapter when we talk about potential energy. I hope that answers all your questions. Have a great day.